Good morning, students. Today we are going to start the fourth unit time series analysis and forecasting methods for predicting process behavior. So, what is time series analysis? Time series analysis is a statistical technique that deals with time ordered data. In process industries, time series data comes from sensors, instruments, and control systems that record temperature, pressure, flow rate, pH, etc. over time. For example, just imagine a reactor. I want to measure the temperature when the reaction proceeds in a batch reactor. Okay, so by using a sensor for every 10 seconds, what is the temperature inside the reactor? That I am just measuring. Okay, so it's just time series data which I am collecting from the sensor. Okay, that is nothing but a time series analysis. It is a statistical technique that deals with time ordered data. With respect to time, we are collecting the data. Okay, the objectives of time series analysis: identify the patterns in process behavior, develop forecasting models, detect anomalies or faults, improve process control and optimization. So, meaning to say, this data will help you to forecast the model, okay, to understand how the temperature is varying inside the reactor with respect to time, okay, and also to detect the variation, anomalies or fault which may come because of some unwanted process or unwanted noise. Okay, so detect anomalies or fault and improve the process control and optimization so that we could able to do the predictive maintenance. Okay, so that's the advantage of having a time series analysis. So what are the characteristics of time series data? Trend, seasonality, cyclic behavior, randomness. What is trend? Long term increase or decrease in the data. So let's say I have given example a batch reactor with respect to time. By keeping a sensor inside it, I am just measuring the temperature for every 10 seconds. Long term increase or decrease in the data. So whether my temperature is increasing, okay, so it's a long term increase, and or whether the temperature is decreasing. For example, if the reactant which has been happened inside the reactor is a exothermic process, obviously as the product forms, the temperature will increase. And when the if it is endothermic process, obviously the temperature we need to supply so that the temperature will decrease. Okay, so seasonality, regular patterns repeating at fixed intervals, whereas the cyclic behavior is a irregular pattern occurring in irregular intervals, often linked to the economic or process cycle. So next one is randomness, that is noise. Irregular fluctuations not explained by the model. So when we see an example, to find the observed value, we will have trend plus seasonality plus cyclic plus error. Okay, so the example for this time series analysis: in a chemical reactor, temperature data recorded every 10 seconds over 24 hours. Just imagine, for every 10 seconds, the temperature has been recorded. We'll have a trend. For example, if it is an exothermic process, warm up. Okay, so is a trend. This is a possible cycle. For example, is a cyclic behavior, is a process cycle, batch operation. So every 2 hours, I'm just doing it. So the batch between the thing time may be vary. Okay, so batch of operation is for 2 hours. So the next cycle may be lag, maybe an half an hour later or maybe a 40 minutes later. So it's a possible cycles. And the noise is the sensor fluctuation. So the characteristic of time series depends on, okay, trend, seasonality, cyclic behavior, and randomness. So the observation at time t. So in a batch reactor, I want to measure the temperature for every 10 seconds. So my observation with respect to time is the temperature. So y suffix t. So the small suffix t here refers the time. So t is the trend, s is the seasonal, and C is the cyclic, and E is the error. That is because of the fluctuation or noise. Okay, so this is a component of the time series models. So the equation goes like this: yt, the observed value of the process at time t. Example, it may be a temperature or pressure. So in the last example, I mean in the previous thing, what I told is a batch reactor with respect to temperature. For every 10 second, I'm just measuring the temperature. Similarly, we can also do for a pressure. For example, I want to measure a pressure inside a distillation column, okay, or a absorption column. Okay, so I would like, even for the batch reactor, I want to measure the pressure inside a batch reactor. Okay, so the observed value either maybe temperature or pressure with respect to time. Okay, so the tt is the trend component showing the long term progression of the series. So the slow increase in temperature due to equipment wear. Example. So it is slowly is the trend component is showing increasing trend, but is a very slow progress, slow increase in the temperature due to equipment wear. That is an example they have given here. Okay, it may be increased value trend or maybe a decreased trend. Okay, the second one is seasonal component is a regular pattern representing the regular pattern that repeat over known fixed periods. Okay, maybe for example it is a daily basis or weekly cycles. Okay, it's a seasonal behavior. Okay, the cyclic irregular pattern. So the cyclic component which captures fluctuations over irregular or unknown length, often linked to the process or economic cycles. So the last one is the noise or the error. The term error term or residual, which accounts for random noise or variation that cannot be explained by the other components. Okay, it may be a sensor fluctuations, okay, or maybe for some other error. Okay, so that cannot be predicted by the any component, by any other component. Okay, hope you understood what I am trying to say. So the component of time series analysis. So here they have taken a temperature in a distillation column, not in a reactor. They have given a scenario monitoring the temperature of a distillation column, top product every hour. So let's say you have time period 1 a.m. early morning, 2 a.m., 3 a.m. So the temperature, observed temperature at that particular time period is 75, 74.8 and 74.7. So it's a declining trend. So over weeks, the temperature is slowly rising due to fouling on the heat exchanger surface. So heat exchanger, because of the heat exchanger surface, over weeks the temperature is slowly rising. Okay, but here is decreasing, right? So they have given a, let's say is rising. Okay, here is slowly decreasing due to fouling on the heat exchanger surface. So here this one is a over weeks, but here is a time period. So if when you see here, the time period is a slowly decreasing, but the trend is over weeks, the temperature is slowly rising due to fouling on heat exchanger surface. Seasonal, there is a daily drop in temperature every early morning. Okay, there will be a dip in the temperature due to the cooling water temperature fluctuation. Cyclic, every few weeks maintenance operation cause process disturbances. Because of that, there is a temperature variation. The error, minor sensor noise or unexpected fluctuations. When you see here at time 3 a.m., the temperature is 74.7. Okay, but the 3 a.m. is supposed to be assumed as 74.5. Okay, and the seasonal variation, seasonality is there is a decrease in morning dip is minus 0.3, and irregular fluctuations, that is what you called cyclic behavior, maintenance operation cost process. Okay, so they have given zero point 0.4 and the error is 0.1. So that at the temperature at 3 a.m. supposed to be 74.7, right? So we got initially at time t trend shows 3 a.m. is 74.5, but the observed value at 3 a.m. is 74.7. So understanding these components allow the process engineers to detect the fault or deviation from the expected pattern. So what is why we need to do this component analysis times component of time series models? Because to detect the fault or deviation from the expected pattern, forecast the future values using the historical data, improve the control strategy so that we can preliminarily, before we can take a preventive action. Okay, that's the idea about it. And coming to the methods of time series analysis, we have four methods. One is classical decomposition, smoothing techniques, and moving average. Okay, and the third one is auto-regressive model, and fourth one is machine learning approach. These are the four methods. Coming to the first method, the classical decomposition. So we have two categories. One is additive model and another one is multiplicative model. So the observed value may be taken from the trend plus seasonal plus error is a plus, that is the additive model. Okay, whereas in the multiplicative model is a multiply seasonal variation, okay, or the error variation or the trend that need to be multiplied is a multiplicative model. Coming to the smoothing technique, we have two smoothing technique. One is moving average and another one is exponential smoothing. So we will see an example for all these methods. Okay. So the moving average, weighted or exponential, are useful for noise reduction, and similarly exponential smoothing, that is a single exponential smoothing, odd linear trend method, old winters method. Okay. So it will handle trend only. Old linear trend method handles trend only, whereas old winters method will handles trend and seasonality. Okay, seasonality. Coming to the classical decomposition, that is additive model and multiplicative model, you just see an example. Here is the heat exchanger outlet temperature. So the example for classical decomposition, the trend over time, fouling in the exchanger causes outlet temperatures to slowly rise. So there is an increase in temperature because of the fouling nature. Fouling in the exchanger causes outlet temperatures to slowly rise. Seasonality, night shift tend to reduce the steam supply due to demand from other units. So there is a variation in seasonality. The error, small fluctuation due to sensor noise or control valve friction. Okay. So if you see here, using the additive model, if changes are roughly constant in magnitude, use of multiplicative model if the impact of seasonality increasing with the higher temperature. When need to go for additive model, when need to go for a multiplicative model. If the changes are roughly constant in magnitude, then we need to go for a additive model. If the impact of seasonality increases with higher temperature, okay, then we need to go for a multiplicative model. Example for evaporation effect. Okay, so coming to the moving average. So the moving average is coming under the category of smoothing techniques. Okay, so the smoothing techniques, again they have three categories: simple moving average, weighted moving average, and exponential moving average. Equal weight to pass n values. So they have given an example for here for moving average. For example, we are collecting a minute-wise flow data. Let's say you have a flow meter. For every 10 seconds, I just would like to know how much is the flow rate. Okay, whether there is a fluctuation in flow rate or not. Okay, even digital flow meter is available nowadays. But it's noisy due to turbulent condition. So a 5-point moving average smooth out the random jumps while preserving the overall trend. For example, this one, for every 10 second or every 5 seconds there is a fluctuation is there. Okay, for example, if you keep in a weighing machine, there will be a, it takes some time to find out the reading exactly, right? So the 5-point moving average smooth out the random jump, okay, while preserving the overall trend of increasing or decreasing the flow. So the overall trend will be maintained. That's the main. So weighing balance, for example, there will, if it is not working properly, if it is not calibrated, you will find a lot of fluctuation. Very difficult to find. So similarly, the flow meter. Let's imagine for every 10 seconds you are measuring the thing, but the flow average is not exactly showing the thing. So if you take a 5-point moving average, smooth out the random jump while preserving the overall trend of increasing trend or decreasing trend of the flow. Okay, so hope you understood what I am trying to say. And coming to the exponential smoothing, single exponential smoothing or odd linear trend method or volt winters method. As I told you, odd linear trend method is accounts only for trend, not seasonality, whereas the volt winters method handles both trend and seasonality. So the predictive values, that means the target values, okay, is equal to trend plus seasonality plus error plus what is that? Trend plus seasonality plus cyclic plus error. Okay, but smoothing means I mean average additive or multiplicative. Addition means you have a plus trend, multiplication multiplicative, right? So single exponential smoothing. The example is pressure in a surge tank under normal operating conditions. Whereas in the odd linear trend method, example is gradual increase in reactor jacket temperature due to scaling or sensor drift. So there is no seasonality, only the trend has been accounted in the old linear trend method. Whereas in the old winter method, it will account for both trend and seasonality, monitoring oxygen uptake in a fermentation reactor. So the trend is biomass growth increases with respect to oxygen consumption. Seasonality is daily operation schedule affect the aeration parameters. Example, reduced air flow rate at night. Okay. So daily operation affect the aeration parameters. So reduce air flow at night. So we need to consider for odd winters method both trend and seasonality. So coming to the method of time series analysis, there are two methods which we have broadly discussed. One is decomposition method and another one is smoothing method, average method. So under that you have a moving average, single exponential, volt method, volt winters method. Okay, so this all there is an example in case of chemical engineering perspective. It has been stated here. Coming to the additive and decomposition process with the linear sensors and trend effects. Okay, whereas in the multiplicative decomposition process where fluctuation scale with the trend. Example, glass flow changes with the load. What is moving average? Smoothing noise in flow, pressure or temperature readings. So coming to the volt method, where is a trend only considered, whereas volt winters both trend and seasonality will be considered. So volt method fouling trends in heat exchangers, whereas in volt winters batch fermentation with predictive daily variation is an example in terms of the chemical engineering perspective. Okay, hope you understood the methods, two methods which we have seen. Now another two methods also we have. Another one is auto-regressive model and machine learning approach. So the method of time series analysis, decomposition, average, moving average, and then auto-regressive model and machine learning approach. So machine learning approach you know already, regression tree, random forest, support vector machine, regression, okay, artificial neural network, long short-term memory network. So this LSTM is a long short-term memory network, especially used for complex problems, long memory data like chemical batch process. Okay, coming to the auto-regressive model. So we have a auto-regressive, that is a moving average or moving auto-regression, regressive integrated moving average. Okay, let's say the auto-regressive terms. Okay, P is equal to auto-regressive terms, whereas D is differencing and Q is the MA, moving average. Okay, so the seasonal arima adds seasonal components as well. So we need to consider to predict the time or temperature of that particular time. So we need to add here factors, moving average. Okay, okay. So y t minus 1, phi 2, t minus 2 and so on and so forth plus error. Okay, first one is AR terms, auto-regressive terms plus differencing. Okay, differencing and moving average terms. Okay, PDQ is widely used, ARIMA. Coming to the steps in the time series forecasting. So time series forecasting, data collection, gather historical process data. Previously, for example, in a batch reactor with respect to time, how much is the temperature every 10 seconds. Visualize the pattern, okay, by plotting the temperature with respect to time. And pre-process, if any anomalies or any cyclic behavior, irregular intervals, okay, then pre-processing the data or noise, okay, noise will be removed in the pre-processing. Stationary, stationarity check, use augmented Dickey-Fuller test. And model selection based on the data behavior, model fitting, train the model using historical data and validate the model. Test performance unseen data, root mean square error and absolute error, mean absolute error. Okay, root mean square error, mean absolute error. Forecasting, make prediction of our future values, performance monitoring, adjust model over time. So application in process industries, predictive maintenance, quality control, process optimization, energy forecasting. Very, very important. So what is the application of time series analysis? Okay, what are the components which are present? Okay, how to identify these patterns? Okay, and predictive what is the application? Predictive maintenance. So that we could able to reduce the things which is going to happen, or rectify the things which is going to happen. Okay, so predictive maintenance, detect equipment wear or failure. Quality control, monitor the product specifications. Process optimization, adjust control set points. Energy forecasting, anticipate consumption load. Chemical engineering example, in a distillation column, time series of top product purity can be forecasted to maintain the optimum reflex ratio. And tools and softwares which have been used for this, okay, time series analysis: Excel for a very basic thing, for basic time series forecasting. Python can be used for advanced analytics: pandas, stats models, profit, scikit-learn. Okay, these are the things which are available in the Python. Okay, MATLAB and R programming, industrial tools like Aspen and PA system, OSI soft, etc. Okay, I even myself I'm not very familiar with a industrial tool like PA system or R programming. Okay, even Python, because you might have studied actually Python in your undergraduate level. I mean, think when we were studying undergraduate, we used to study Pascal and C and C++. Okay, so because of the language, okay, the computer language it is updated, and we need to, it is easy to follow the things. I mean, it's become easy, right? So the programming language become very easy when compared to the previous old models, and it has a more sophisticated computational, um, can handle the long complex problems. Okay, and coming to the challenges and consideration: non-stationary data, data quality, model overfitting, interpretability, real-time forecasting needs. What are the challenges when you go for time series analysis? Non-stationary data require differencing or transformation. Data quality, missing values, noise or outliers are the challenges. Model overfitting, especially when we do by machine learning approach, then we may give a overfitting. Interpretability, machine learning models can be a black boxes. Real-time forecasting needs, okay, fast computation and model updating. So as I told you, this programming language are for fast computation as well as model updating. So we need to go for that things. Coming to the case study for the batch fermentation process, let's say the biomass concentration is varying. Okay, pH and temperature you are taking. Forecast the pH drop to preemptively add buffer solution. So when the pH, so I want to try to measure the biomass concentration, pH and temperature. When the pH temperature during the process of fermentation is decreases, or the pH drop, forecasting pH drop to preemptively add buffer solution. So otherwise what will happen? The fermentation will not be effective when there is a drop in pH. Okay. So use long short-term memory network for non-linear time series forecasting. Okay. Outcome is improves process yield by 15%. So that is a control, by using a control of identifying the drop and then adding a pH buffer. Okay. So that buffer solution, so that the pH will be increased, so that there won't be any decrease in pH, so that we can maintain the optimized process point of the fermentation process. And coming to the application of time series analysis, I just try to take three examples in the application in chemical engineering perspective. The previous one is also a very good example only. Okay, so process monitoring and fault detection. So application is monitoring the reactor temperature or pressure over time. How time series helps? By analyzing the historical trends and detecting deviation from normal pattern, engineers can predict the equipment malfunction, runway reaction or control loop failures. So by knowing the historical trend and detecting the deviation from the normal pattern, so one can easily predict the equipment malfunction. So that's it. So time series analysis helps in the process monitoring. In a continuous state tank reactor, the example is ARIMA. ARIMA is an auto-regressive integrated average. Okay, so what I told actually, auto-regressive integrated moving average. Okay, so ARIMA or control chart based approach can help the flag this as a potential early fault. So that is a process monitoring. The time series analysis will help us. And the second one is the energy consumption. Let's say predicting the steam or electricity demand in a chemical plant. Usually in any industry, there is a large quantity of demand will be the electricity, electrical demand for any equipment which need to be operated with the electricity only. Okay, so in that case, so we how to generate the electricity by predicting the how much the steam need to be produced, predicting steam or electricity demand. So how the steam can be produced by by running a boiler, right? So for that energy supply is needed. So we need to predict the steam or electricity demand in a chemical plant is a must. Forecasting daily demand or hourly consumption helps optimize the boiler operation or purchase from external grid or reduce the operational cost. So meaning to say, daily predict the things. Forecasting daily or hourly consumption helps optimize the boiler operation. So using volt meters, so it's trend as well as the seasonal variation. The utility department can predict the steam demand based on the past usage pattern, that is a time series data that show a daily seasonal cycle and a long-term trend from increasing production. Okay, so this is an example for the time series data for the energy consumption. Predictive maintenance. So let's say vibration monitoring of pumps, compressor and turbines. So how time series helps? Time series models detect gradual changes in vibration signals or frequency content that perceive the mechanical failure. Analyzing the structural signature over time from a centrifugal pump helps forecast the bearing wear. Techniques like Fourier transform combined with time series smoothing allow scheduling maintenance before failure occurs. So this all for will help you to do the predictive maintenance or to optimize the process or energy consumption or process monitoring. That's what I just try to give an example for all these three categories. Okay, with this I would like to conclude today's section. So what we have seen in today's section, what is the time series analysis, what is the application of time series analysis, how the component, what are the components of time series analysis, okay, what are the factors, okay, the four methods which we are talking about: moving average, arima, okay, classical composition, decomposition, smoothing techniques, and method of time series analysis, another auto regression models and machine learning approach. Okay, so hope you are clear with this time series analysis. So this all will help you actually be, the thing is same, the data need to be collected and what you call the steps which has been involved: visualization, pre-processing, stationary chain, model selection, and then fitting the data, training the data, validation, forecasting, performance monitoring. This is all about the machine learning models, and they're all part of the parcel of the machine learning. Okay, so this need to be done. So in order to collect the data and then try to find it out, time series analysis is a part of thing which we are collecting the data. So most of the time when the people do modeling, they may expect a large amount of data. Okay, so the how to get the data by using the sensors and as I told you, is a statistical technique. Okay, so to collect the data by using some instrumentation. Okay, with this note, I would like to conclude today's section. If you have any doubt or anything, please feel free to ask me during the face-to-face section. We have one more section actually on next week. Before that, I will try to complete the units. Okay, the syllabus for the thing, and the syllabus for your FAT 3 most probably will be, I mean, the FAT 2 is 3, 4, and 5. So with this note, I just conclude today's section. Thank you for your time.